Hello everyone, and welcome to the Modern Java course. Last time we talked about ReentrantLock and other threading concepts. I hope you checked out that video. Today we will dig even deeper into the power of modern threading APIs in Java. All this applies to virtual threads as we have in Loom and to the standard native threads. If you want to learn about these, I made a video specifically dedicated to Loom in this playlist. Before I proceed, as usual, the code for this and the other videos in this series is available in my GitHub page, so check out this project, star it, and follow me on GitHub. Up until now, we focused on ReentrantLock, which offers some improvements to synchronized while keeping a similar set of semantics. We also have read-write-lock, which is implemented by ReentrantReadWriteLock. This type of lock is in fact two separate locks, one for reading and one for writing, as we can see here. In the previous synchronization code, we had one lock. That is not as efficient as it could be. When adding a name, we always need to lock. However, when we can have multiple threads reading from the list at once, there will be no overhead for that. The reason we do that locking is that during list modification, we cannot read from it. The read-write lock solves that common situation. Multiple threads can hold the read lock and run concurrently with no issue. If you try to obtain a write lock, the read threads need to be released. Let's explain this again visually. Let's say I have a variable like this. I also have three threads that want to access that variable. With a normal synchronized or reentrant lock, I can create a lock and block these threads so only one of them will be able to access the variable at any given time. This seems good, but it's also slow. What if the threads want to read from the variable and not write to it? In that case, synchronization is redundant. Reading is safe. With a read-write lock, things are very different. A read lock lets all the threads go right through it normally. It's pretty much a free-for-all. Every thread can read right away. Multiple threads can reach your code. It's almost as if it isn't there. So it's much faster than typical locking code. That makes sense if everything we need is just reading. There's really no need for locking. Let's say thread 3 invokes code that needs to write to the variable. In that case, it tries to grab the write lock. Notice that in this case, thread 1 and 2 are both holding the read lock. So the write lock will wait for them to release their read lock. Once they released their read lock, no additional reads will be granted. All threads will be locked outside and the write lock will be granted. Then the thread will be able to change the variable value without worries that another thread might be reading the value at the same time. This is far more efficient as read operations are often more common than write operations. As a result, performance can be much faster than typical locks. Going back to the code, we can see we have two methods. First, we have the add name. It modifies the list of names, so we have a write lock on the block. Notice the code is pretty similar to the regular lock code, only it uses write lock call. When this block enters, other locked code in the class won't execute. Specifically this code. The isInList method is probably invoked all the time. It will just block when the write lock is in effect. But if the write lock isn't active, then this method is free for all. All threads can just go in and read whatever they want. This is a powerful tool. Still, the Reentrant read-write lock suffers from some shortcomings. If you obtain a read lock, you can't upgrade it. Let us say we want to keep names unique in the previous code. We don't necessarily need a write lock. The name might already be in the list, in which case we don't need a write lock. But if we do end up needing a write lock, we won't be able to get it without relinquishing the read lock first. It doesn't support optimistic reads and isn't as efficient as it can be. StampedLock solves these limitations. The API for this type of lock is slightly different than the other locks and provides the ability to upgrade or downgrade the lock. Unlike standard locks, stamped lock returns a long value that we need to use to release the lock. For most cases, it's better to use this API than the Reentrant read-write lock. For simplicity, let's first look at the read lock. Unlike the previous code, we get a long value representing the stamp, which we then release just like a standard lock operation. This approach lets the thread avoid thread local storage and is slightly faster. It also gives us a handle value that we can then use to do interesting things. In this version of the add names method, I implemented a unique optimization just to show an edge case. Let's say I have a list of names where I don't want to have duplicates, but in many cases the method is invoked with the duplicate. In this case, I can grab a lock, read lock as I do here. Then I can check if the name is already in the list. Assuming that in most cases it already is, I can return and release the lock. In these cases, I would have avoided the expensive write lock completely. But if it is contained, then I would need a write lock. With a typical Reentrant read-write lock, I can't get a write lock while I'm holding a read lock. I would need to release the read lock and then get the write lock. But here I can convert the read lock to the write lock, which would be potentially more efficient than grabbing and releasing a read lock before acquiring a write lock. For most cases, the stamped lock is the best option for a lock, but it doesn't support conditions. That's where Reentrant lock is still king. But there's one caveat to notice in stamped lock versus Reentrant lock. They aren't Reentrant like synchronized is. What does that mean? If my current thread holds the lock and I try to acquire it again, this will work in a Reentrant lock. But the stamped lock won't let you acquire a new lock before releasing the existing one. So if I change the code here to invoke isInList, will be a deadlock, since the isInList method will try to acquire stamped lock and stop. The event system we outlined in the previous video can be adapted to use conditions with code such as this. I trimmed a lot of the excess code from here, but basically conditions are signals similar to wait and notify in the object class. This is a bit confusing since we need to use the await method instead of wait. We need to use signal instead of the notify method. Other than that, they are almost identical to the wait and notify calls. The main benefit is that they can be used with locks. That means they can enjoy the other features of locks that we previously discussed, such as read and write locks, etc. Several classes in the concurrency package fall under the banner of synchronizers. The most common among them is the semaphore, which is a classic concept in concurrent programming. A semaphore is a system of flags used to signal information in the old days. Most importantly, semaphore is raised to stop a train from entering a busy station. The semaphore class in Java limits the number of threads that can enter a block. This is useful if a resource can become a bottleneck. A good example would be a database which has a limit on the number of concurrent users. We can use a semaphore to restrict access and prevent overuse. This example allows 20 threads at most into the body of the restricted area. The countdown latch can wait until the count reaches 0. Imagine a situation where we have multiple threads that need to complete tasks so that our code can proceed. How do we know they are all finished? We use the countdown latch to count, and when it reaches 0, the await method will release our current thread and indicate that we're all done. Here we define a latch that counts to 10 threads. When a thread finishes its work, it invokes the countdown method, which reduces the latch by 1. When the count reaches 0, the await method stops blocking and all 10 threads completed execution. The exchanger class lets two threads exchange objects. It provides a synchronization point where two threads can pair and swap elements within those threads. Here's an example of two threads passing data in both directions. This call sends the string list variables to a different thread and waits for a response. Here we read the response and send back null. This is helpful when two threads are collaborating and need to exchange data. The atomic package contains multiple atomic classes for handling single variable atomically without risking concurrency issues. This is typically the case for primitives in Java, especially if they are marked as volatile. But this is not guaranteed when multiple threads change values concurrently. This code is the best possible way to demonstrate how important it is to use an atomic variable. In this code, we loop over 1,000,000 times on a variable and increment them all without a lock. We do this with 20 concurrent threads, so every variable should print out 20 million in the end, but they don't. This is the result of running this code on my M2 machine. A primitive is atomic, but only when reading the value. Once we start modifying the value, we have a problem. Even volatile doesn't really help these cases. Object wrappers aren't thread safe, and in fact, pretty horrible, as you can see from this number. Making them volatile is also useless, although we can see the impact of volatile. Notice the enormous difference between the correct atomic result at the end and all the results that preceded it. This is especially true for object types, which performed particularly badly. Synchronization or locks can solve these problems, but this package is simpler. The notify and condition code from before is bad. It is long, verbose, and hard to understand. It would be even worse if we needed to return a value. There's got to be a better way to spin something into a separate thread and get a result. There is, and it is a system that is common across many programming languages, known by the name Future and Promise. The Java Promise API is named Completable Future. It was introduced as part of Java 8. A future represents the result of an asynchronous computation. A completable future is a future that can be explicitly completed. In this code, we run on a separate thread and return a result. We create a single thread executor, which means all operations will run on one thread. We would use a thread pool or a virtual thread executor to create multiple threads. Notice that the executor argument here is optional, but this is only a teaser of the full power of this API. The challenge of asynchronous code is in dependencies. We often want to implement a flow that starts in one thread moves to another thread, and asynchronously returns the result to the final location. There is one limitation though. You will notice that the previous code had try-catch block that wasn't really handled. Where did that exception go? This is where stages come in. A completable future is comprised of multiple completion stage instances that we can assemble using a builder pattern. We can daisy chain them to create a process that implements multiple stages. A simple example of this could be this, but there can be far more elaborate examples, such as completable future all of, which binds together multiple completable futures into a single operation that we can treat as a single future. This doesn't return a result, but helps us wait for multiple futures to complete by using the join method. One of the most common problems in concurrency is for shared sets of elements. Java 1.0 had some collection classes, specifically vector and hash table. Both tried to be thread safe and both didn't do a great job of it. Their use is discouraged in modern Java. There are solutions for making the existing collection classes seem thread safe, specifically collection wrapper methods, synchronized collection, synchronized list, and synchronized map. Those are all decent solutions for simple use cases. But if a collection needs to scale to high throughput and more nuanced support, then this might not be enough. The copy on write array list and copy on write array set work as a list or a set implementation. They are mainly useful for a collection in which very few mutations are made, but read access must be very fast. In these collections, the access to the elements is fast and unsynchronized. Mutating operations change a different data structure, which then replaces the entire list or set in one atomic operation. This means changes are significantly slower than a synchronized array list or array set. However, reads are almost as fast as unsynchronized version. It is hard to tell if this is a trade-off that makes sense for most developers, so you will need to benchmark your code to make a call. These and the other collections in the concurrent package don't throw a concurrent modification exception and might allow a stale iterator to proceed. Concurrent linked queue is a thread-safe, unbounded queue that uses linked nodes to store its elements. It is an implementation of the blocking queue interface. One of the main advantages of concurrent linked queue is that it does not require any locking or synchronization to add or remove elements from the queue. This makes it a very fast and efficient queue implementation, especially in multi-threaded environments where many threads may be accessing the queue concurrently. There are several additional concurrent collection classes in Java that are designed for use in multi-threaded environment. Here is a brief overview of some of the most used concurrent collections. Concurrent hash map is a thread-safe implementation of the map interface that uses a hash table data structure to store its elements. It is similar to the hash map class, but it uses locks to ensure that only one thread can modify the map at a time. Concurrent linked DQ is a thread-safe unbounded double-ended queue that uses linked nodes to store its element. It is an implementation of the DQ interface and is based on a linked list data structure. It supports efficient insertion and removal of elements at both ends of the queue. Concurrent skip list map and concurrent skip list set are thread-safe implementations of the sorted map and sorted set interfaces that use a skip list data structure to store their elements. They are similar to the tree map and tree set classes, but they use locks to ensure that only one thread can modify them at a time. The Threading support in Java has evolved dramatically over the past decade. Java leaped to the forefront of the industry by virtue of its built-in threading support. However, it fell behind as that support became a hindrance. Modern versions of the API fix that and currently offer unrivaled constructs for dealing with concurrency. Follow through for the next video where I continue the subject and dig much deeper. If you have any questions, please use the comment section. Thank you.